for someone.
Come again, please. I lost you there for a moment.
Okay, so we will begin now.
Okay.
Okay. So first off, I want to welcome Lorenzo Tamellini. That is a long-term collaborator of mine. We have known each other for 10 plus years now. And he finished his PhD in 2012 from Politecnico di Milano under supervision of Professor Nobile that gave a talk this morning. Then he did a postdoc at EPFL until 2015, and then he continued on to join the CNR IMATI, because it is one of these international, national research institutes that is focusing on applied mathematics and information technologies. And yeah, so Lorenzo, if you would give us the pleasure of starting. Thank you.
Okay. Just before I begin, I'm given 1 hour in total, so that would be like 45 plus 15 or so, I guess.
That's perfect.
Okay, good. Let's see how good we go. So thanks for having me. Sorry I couldn't make it to KAUST. I've been there many times, but I haven't been there in a few years now. It would have been nice to be, but next time. So you have the title here on this slide. It's multi-stochastic collocation, which is, as the title says, a multi-fidelity method for a certain quantification problem. So here's the outline, of my talk. First, I will introduce multi-index stochastic collocation, the method, which, as I said, is a multi-fidelity method for parametric PDAs. And the too long didn't read version of it is MISC, multi-index stochastic collocation, in practice extends the well-known sparse grid stochastic collocation method for UQ by adding one or more indices for the spatial discretization. So in the same machinery of sparse grids, you also now throw in control on the mesh size, on the step size, and possibly other discretization hyperparameters. And out of it, what we get is an approximation of the moments of the quantity of interest of the PDE, but also, I argue even more importantly, we get a response surface for the quantity of interest that we can then query and bid for subsequent UQ analysis. Then this is part one of the talk, and then on part 2 and 3, I want to give you the flavor of a couple of applications we've been working on recently. So one is an application to naval engineering, and the third one is a very recent thing that extends MISC to multidisciplinary system. There would be systems where your focus is not just on one PDE, but maybe on a bunch of equations linked together, like a PDE model that outputs a quantity that gets input to another PDE or ODE that gets input into another PDE, or maybe an even algebraic system. So it's a multidisciplinary thing, and there's a point in using MISC into this framework. So MISC is something that's been going on for a while now. The first work on MISC was prepared in 2015, 2016. Abdul Latif was still a PhD at KAUST back then. And then Raul and Fabio were involved, and also Joachim, of course, came in. And here you see instead the names that I've been working on the applications. So the naval engineering problem is with Chiara Piazzolla. She's a postdoc at IMATI also. And this other bunch of guys are all colleagues that work at the Naval Engineering Institute of my research facilities. So the CNR Institute of Naval Engineering in Rome. And then here you see the names that have been working on extensions of MISC multidisciplinary systems. You might see a bunch of known guys here, John Jakeman, Alec Rodetsky, Michael Eldred, Simon Friedman, and Doug Allaire. So let me, now that I'm done with this introduction, let me start with part one, where I introduce how MISC works. I mean, I thought I would not spend too much time on the generic uncertainty quantification problem that will be preaching to the choir in this audience. So I'm just going through a couple of lines here just to set the notation, okay? So imagine you have a PDE on an ODE, it doesn't really matter at this point. This PDE depends on a bunch of random parameters, let's say n capital random parameter, n capital uncertain parameters, Z1 to Zn, and the output of this PDE is either its solution or a functional of the solution. In general, we call this F. So F is our quantity, is a function of the uncertain parameters. It's an n-dimensional function, and it's known implicitly. We don't know the expression of F. We only know the dependence of F through evaluating the solver of the ODE or PDE. And now, for MISC, it is crucial to assume that the PDE depends on a bunch of hyperparameters. Here I say in this, throughout the talk, I use R as the number of hyperparameters. So as I said, the hyperparameters might be mesh sizes, can be more than one mesh size. If you have like a finite differences method or a finite volumes, maybe you are free to play with the width and the height and the depth of each element independently. So we would have up to 3 mesh sizes. There's time steps, there's tolerances. It's a bunch of hyperparameters. Now, let me introduce now 2 multi-indices. The first multi-index is alpha. It's a multi-index with R components and prescribes the values of the hyperparameters. So alpha 1, 2, 3 means, for instance, that we have 3 different mesh sizes, and we select the mesh size given the value of alpha. And the same goes for beta. Now, beta instead is a multi-index in n components. So there's n integer numbers, and these n numbers control how we sample the space of uncertain parameters. I'm going to give you an example in a second. Here it is. So F sub alpha beta. Can you see my mouse, by the way? What if I do this? Can you see my mouse moving? Hello?
Hello? Yeah, yes, we can see it.
Okay, good, great. So now F sub alpha beta is the corresponding approximation of the PDE. So here you see a picturesque representation of what would be, for instance, F sub 416,439. This would be the solution of my PDE evaluated over this mesh that has 4 elements in this direction, 16 elements in this direction, and 4 elements in the other direction, which I evaluate over 3 times 9 samples in the parametric space. Okay, so I'm solving 27 PDEs on this mesh, which is denoted by 416,4. Okay, I'm sweeping a lot of things under the rug here, but just to give you the idea, right? Now, as I said, I'm gonna go towards sparse crits somehow, and you might know the sparse crits depends on a multi-index set. So instead of just running one simulation, one F sub alpha beta, where all the components of alpha are large and all the components of beta are large, there would be one simulation where I have a very fine mesh and I solve a lot of PDEs on that fine mesh. I want to go towards a sparse crits approach. So I will consider several discretizations. Each of these discretizations corresponds to a different alpha beta, and I will collect all these possible alpha beta indices in a so-called multi-index set, which is a set of multi-indices. Each multi-index has R plus n components, and this multi-index set that collects all of this discretization has to be downward closed. And then I write down the usual, I would say, combination technique formula. Usual for those who are familiar with the combination technique formula. For those who are not, I mean, it doesn't really matter. It's just a matter of putting together this whole bunch of different possible approximations. Rather than running just one, I run many of them, but each of them is substantially cheaper because I never refine everything simultaneously. And then I put together everything with this combination coefficients C that for which I have a formula. So given I get the set I get the coefficient C, I run the simulation and I get the approximation. So, and in the easiest example, now here I have a pictogram just to convey the idea for those who are not familiar with the combination technique. If I strip down everything and boil it down to a problem where I have only one hyperparameter, one mesh size, and one random variable that I have to sample, and I can play with at least, let's say, 4 possible discretization. This would be on this axis here, you would read the alpha multi-index, the mesh discretization. Here you would read the beta, so the number of samples. Each dot here is a different combination of sampling and meshing discretization. The MISC formula says that I can approximate the very fine discretization with this formula here, P plus Q minus C, so a linear combination of these 3 intermediate solutions. I put them together somehow, and I get the fine formula. And if I have more than so R larger than 1, more than 1 random variable, and more than 4 possible combination, I get the multi-index that I want to use by the usual guessed-agreeable algorithm. So here the multi-index would be the simple PCQ, that's the multi-index that we're using. If I'm playing with more stuff, I have an algorithm that runs through all the possible multi-indices and selects the one that I need the most by running a certain, let's say, an heuristic error indicator, I would say. I wouldn't go much more into details than this. So, but it's a very efficient and very known algorithm that's been going on for a while. So in practice, what I have again is a way of reconstructing a full approximation of my quantity of interest that depends both on a number of hyperparameters and on a number of uncertain parameters at a linear combination of many Cursor solutions. And if we do things carefully, by running these algorithms carefully, we balance the solver error, the PDE error, and the, let's say, parametric error. And in particular, sometimes for certain classes of PDEs, we can craft an a priori set I such that we can prove convergent results for this algorithm. And they look as they should, so they look pretty much like sparse grids, results of convergence. We have 2 different flavors. One is for a finitely many number of random parameters. One is for infinitely many random parameters. And yeah, I wouldn't go much too deeper into this. Now, at this point, any solver can be used for solving the PDEs. And as I said, we can accommodate situations where we have more than 1 hyperparameters. And in particular, when we have tensor meshes, where we can play with the discretization step along different directions, like in the case of finite differences or finite volumes. But if you don't have the luxury, you don't have to do it. So even 1 index to select the mesh will do. And in the end of the day, this is just a sampling approach. So even if you're completely lost into the details here, just suffice to say that at the end of the day, you have a list of PDEs that you need to solve for different values of the parameters, uncertain parameters. Some of these PDE solvers will be done on a certain mesh, some on another mesh, and the algorithm gives you which mesh for which parameters. So it's you can just run independently all the solvers and then you put everything together. Again, here, just as another example, for instance, this is taken from the naval engineering problem that I will show you later on. This is a problem where you have 1 hyperparameter, so 1 index to select the mesh size, only 1 mesh size if you want, and then 2 random parameters. I will tell you later which parameters. But here on this pictogram, you see on the left the set of multi-indices that we're using. So each of these dots correspond to a different, let's say, fidelity in space, so a different mesh, and different combination of how you sample the different parameters. So see here, I have, I would say, like a 20 or so. Each dot here corresponds to a different f sub alpha beta from mesh 1. So here I have like 20 f alpha betas, and I put everything together to get the MISC result. And overall, the sampling, so this is what is going on under the hood, this on the left. But if you don't want to understand what's going on here, just take a look here on the right. You see that there's a sampling of the parameter space. We have 2 parameters, this u and this t. And we sample these 2 random parameters in this way. Each dot is a PDE solver. Different colors are because of different meshes. So you see there's a lot of blue and a lot of red and not a lot of yellow and purple. Purple would be the most refined mesh, okay? So this is what happens here, what is going on. Now, before going into more, let's say more engineering applications, let me get started with the usual old friend, the usual PDE, elliptic PDE with random diffusion. This is the domain where we want to solve this elliptic PDE. It's a three-dimensional banana shape, I would say. And this thing depends on three random variables. Depending on these three random variables, you have different realization of the diffusion coefficient. For instance, here you get two snapshots of this random diffusion coefficient. So it's three random variables, so three indices for the beta, and then the solver that we're going to use here, it's an IGA solver, and this solver allows us to play with the three different discretization steps. So we have three hyperparameters, the mesh along this side, the mesh along this direction, and the mesh along the angular direction. So it's three hyperparameters and three random variables. So it's 6 indices in my MISC. And this is the result that we get when we try to compute here the goal is the approximation, the expected value of a functional of the solution. So here you see a bunch of colored lines. The plot shows tolerance versus time. So the flatter is the better because it means that I can push it to small tolerances without having a blow up in the time. The blue and the green are multi-index Monte Carlo, multi-level Monte Carlo. You might know these methods. They are, let's say, other possible methods to do UQ based on Monte Carlo. Here, we are seeing instead the convergence of the red line is the MISC convergence, which is substantially faster than MIMC and multi-level Monte Carlo because we're exploiting the regularity of the solution. So instead of doing Monte Carlo in probability, we do stochastic collocation sparse grids. And the dotted line is the expected convergence rate. So you see that eventually we actually see the convergence rate that we want. So we were pretty happy when we saw these plots. It means that our convergence result is actually pretty good. And again, why would this be good in terms of computational effort? As I said, the point is that you are playing with a bunch of meshes, and the idea of multi-fidelity methods is that you want to allocate most of your PDE solvers, most of your calls to the PDE solver on coarse meshes. So you would explore the bulk, I would say, of the variability over a coarse mesh. And then from time to time, you refine the mesh, but then you only use this refinement to, let's say, to fix the original estimate that you got out of sampling extensively the coarse meshes. You see here, this is the mesh allocation. So take, for instance, the black line. The black line is the mesh allocation that we got for obtaining the last point here on the convergence. This work allocation plot says that we were allocating a bunch of, I would say, several thousand PDEs on coarse and intermediate meshes, and only a few hundred mesh PDE solves on the most refined meshes. So you see there's a factor 10 at least between the number of calls on this coarse mesh and the number on the fine mesh. And this is where we gain a lot of computational effort. Okay, good. Now, so this is the, I will give the reference to this work later on, but this was the general overview of MISC. It's a multi-fidelity method that juggles several meshes and does sparse grids in stochastic in the parametric space. So we leverage on these two things. Now, the first example that I showed you was this, let's say, simple elliptic PDE problem. Now I'm moving to the second part of my talk, where I actually show what happens in a, I would say, more realistic case, where actually we apply MISC to this naval engineering problem. So you see here, this is the boat we're talking about. It's a ferry boat, the one you take to go around for vacations, where you would carry your car on the boat, and then you get on the boat and then takes you to another island, for instance. So this is a ferry boat in straight ahead advancement in calm water. We're interested in estimating the resistance to advancements. 1 second only, sorry. Can you give me 1 second? I need to quit. Okay. Okay. Present slideshow. Okay. Can you hear me again?
Yes.
Yes.
Okay, sorry about that. I had to disable Telegram. Anyways, okay, so here we're interested in the resistance to advancements of the ship, so the drag of the ship. And the drag of the ship, of course, depends on a number of things, and in particular, it depends on these two uncertain parameters that we want to focus on: the speed with which the boat moves. The faster the speed, the more the resistance, in a sense. And the draft. The draft would be the vertical displacement of the ship due to the fact that the ship is being loaded with cars and persons. So the more the ship is loaded, the more it sinks, and then there's more water that it gets in contact to, right? So we assume that these two are uniform random variables. The speed is within the operational range of the ship, and the draft is plus or minus 10% of the nominal design. And these two things are, of course, random because we don't know exactly how fast we go. Depends on the sea state. We don't know exactly how much persons and cars there will be on a certain day. So we need to assess do UQ on the drag coefficient of the boat, let's say. So this is just a quick word on the solver that we're using. This is the computational domain on the left. This red thingy is the boat. This is the computational domain. The boat moves in this direction. So we solve a lot of domain behind the boat to get the wave patterns. And this is the mesh that we're using. You see, it's a very complicated mesh. It's several blocks, overlapping blocks. And these are some simulations that we get for certain configurations of draft and speed. You see here the different wave patterns you get behind the wave, behind the ship. Everything looks fine according to what our engineering colleagues says. So we're confident in going forward. And now I get to the MISC application. So as I said, we want to do UQ on this boat. We consider 4 fidelities, 4 solvers. So in particular, these 4 meshes here. The first one has 11K elements, and the last one has 5.5 million elements. So assuming that the cost of solving the PDE is linear in the number of elements, the last mesh costs about 500 times more than the coarsest one. And the equation we're going to solve is free surface Reynolds average Navier-Stokes. And the solver is a finite volume solver called Key-Navis, developed by our colleagues of the engineering department, the naval engineering department. It's in particular a second-order finite volume scheme. As I said, it can handle multi-block over meshes with overlapping blocks, as I showed you in the previous slide. And in particular, for a fixed mesh, what you do is the solver is a multi-grid solver with V cycles, okay? So the finest level, the finest grid that we reach with the V cycle is our fidelity. So the coarsest fidelity is a solution only on the coarsest grid. The second fidelity is a V cycle between the first one and the second one. The third fidelity is a V cycle from the first one to the third, and so on and so forth, okay? So what I get out of this, okay, I have to tell you that the finest mesh is the only one that the engineers actually did with a CAD. The other fidelities are obtained by the refinement of the first mesh. And in particular, the coarsest mesh is a mesh that would be very bad for any, let's say, one-shot engineering simulation, I was told. So now, again, this is the same plot that I showed you earlier on. And here, again, now it makes a bit more sense what kind of situation we're talking about. Here, you see there's 2 random parameters, speed and draft. And here are the 4 fidelities, the four grids that we're using the V cycle. So you see each of these dots, again, is one component of the combination technique. More combination technique coefficients have coarse fidelity and sample extensively the space of parameters, and the highest the fidelity, the coarser the sampling of the space of the uncertain parameters. And here on the right, you see again the association of each point in the parameter space with the 4 meshes that I showed you, right? 1 being the coarsest and 4 being the finest. This is halfway through the run, and in the end of the run, we got to this situation. So you see that we sample a lot this part, the uncertain space. The sampling pattern resembles a lot what you would get for a standard sparse-grid sampling, sparse-grid stochastic collocation approach. But there's colors, meaning that you solve not all the points with the same mesh. And in particular, the points are nested. So whenever you see mesh 4, there's also a mesh 3 and a mesh 2 and a mesh 1 underneath, okay? Now this is how it looks. And again, there's a lot of blue. So even though we are sampling extensively, the blue is very cheap to solve. It runs on a few, I would say a few minutes, whereas the purple, the finest one, takes a good few hours on supercomputing. So there's impressive speed gain, I would say. So this is the work allocation as the iteration go. And you see there's a lot of blue. So as you keep going, there's more and more simulations on the coarse meshes, and only a handful of simulations on the fine mesh. In particular, at the end of the day, we only have 5 solves at the highest fidelity. Now, how does this one play out? Okay, so this is a convergence result that we get. Now, there's 3 lines here. You focus on the blue and forget about the red, okay? The blue line is the missed convergence, and then the red line, the black line is the reference value that we got with our running for a substantial amount of time, the finest fidelity. We were able to get a decent PCE approximation of the response surface on the, let's say, single fidelity on the highest fidelity. This is the kind of convergence that we get for MISC, the blue line. So the entry cost is fairly small. Here on the horizontal axis, you see computational cost being normalized cost of each solve. So each solve on the coarsest mesh cost 1, each solve on the finest mesh cost 100. So, and then in between. So from here to here, what you do is you actually add 1 solve to the finest fidelity. So what you see is here, we get soonish to decent costs. This is a matter of maybe 1 hour of running or something like that. And then we depart a bit, and we actually don't converge very well to the reference value. I mean, the difference between what we get in the value of reference is not that much. I mean, any engineer would probably buy this method, but still, it's good to see what happens here. And again, this is the convergence of the expected value of the drag of the ship, okay? So the good news is it sort of works and it gets to a good result pretty fast. The bad news is it doesn't converge very well to very small tolerances. And what happens is this. In this particular case, the solver is this complicated multi-grid, multi-block solver. And there's we never actually queried the solver to full precision. We don't have actually access to setting the full precision. What happens is essentially the solutions that we get out of those solver, they are not fully resolved. So instead of getting the exact value of the solution, we get an approximation, a noise approximation. That noise enters gets interpolated by MISC. And then what happens is instead of getting a nice, smooth response surface, we get this bumpy thing, which gets the main trend, but it's disturbed by this crispiness, which is again due to the solver noise getting interpolated. Okay, and this is what prevents the convergence up to a certain extent. And again, here I'm showing you for the benefit of giving you an idea. This is the highest fidelity surrogate that we use for the surrogate for the highest fidelity. Here you see that there is no visible noise, whereas here on the this is the surrogate for the lowest fidelity. You see that there are bumps. There's a bump here, a bump here, a bump here in the middle. These are due to under-resolved iterations of the RAND solver. I can give you more details on this, but essentially the tolerances that we play with, they don't resolve exactly the problem. So we get this noise, then we then interpolate. But add to this noise, which we want to get rid of, and we have a research line going on this, we sort of get a good rule of thumb result. So this would be the PDF of the drug that we get out of sampling the surrogate model. So getting this PDF is just a matter of sampling with Monte Carlo extensively this response surface, and then using, for instance, kernel estimator density or histograms. And of course, there is this spurious peak that is due to this roughness on the surface, but the overall trend is good enough for engineering purposes. It has this shape. You see that there's a skewness in the distribution. I mean, the engineers were happy anyways. And then, of course, we have ideas on how to fix this problem of the noise. So this was just to show you how MISC can actually be employed on I would say, realistic problem. And finally, I want to give you an idea of how we can extend MISC to multidisciplinary problems. So you see, I'm swiping a lot of things under the rug, but there's room for discussion if you want. Then after the end of the talk, I'm happy to give you details and listen to suggestions if you have. So what is a multidisciplinary system? For instance, this is a multidisciplinary system. We have 4 models that are coupled. This is an economics model for a gas turbine, for the performance of a gas turbine. The heat transfer. So there's a turbine blade that gets deteriorated due to the heat generated in the turbine. The heat impacts the lifetime. The lifetime of the lifetime impacts the economics, and the economics is also impacted by the performance. Each of these blocks depends on a bunch of uncertain parameters: Z1, Z2, Z3, Z4. These are exogenous random variables that we know. I mean, we know their PDF, and then each block, each equation passes to the subsequent equations certain quantities, and these are also, so Y1 is the input of the heat transfer that gets to input in lifetime. So lifetime has input Z known and input Z unknown, and we call these unknown inputs coupling variables, because indeed they are coupling random variables. The main difference with Z is that we don't know the PDF of Y's because they are known only after doing UQ on the previous model. And the goal is overall to do UQ for the final output of the system, for this Q, which is the final output of the economic system. And here, I mean, I've chosen to show you only systems with feed-forward coupling, but the method that I'm going to show you later on can also accommodate feedback. So, for instance, performance and economics might be linked in a feedback form, where economics feedback to performance, for instance. I'm just not gonna give you details on the feedback for the sake of time, but everything works fine even in the case. So let me give you a couple of more details on how this system of multidisciplines, each block here is a discipline. Let me give you a couple of words more on this multidisciplinary problem, and then I will dwell a bit into how we use MISC in this scenario. So the first one, again, this is a gas turbine application, and the first discipline is a heat transfer, which models the heat dispersion over each blade of the turbine. So this is a cross-section of the blade of a turbine. Gas flows outside the blade. There's coolant fluids in the cavities, and we need to model the heat propagation on the metal, let's say, part, which we did a color part here. So this is the metal frame, the metal structure, okay? And this model depends on a bunch of uncertain parameters: the diffusion, the heat, the transfer coefficient of the metal, the heat diffusions of the coolant fluids, the heat here at the top and the heat here at the bottom of the blade. And all we care about is actually the bulk temperature of the blade. Okay, so the output of this model is the bulk temperature of the blade, which then gets input into a lifetime model for the turbine. So the time until the blade fails. Okay, and so there's this formula, proposed by these two persons. This formula depends on the bulk temperature, depends on this coefficient, which is uncertain, and the output is the failure time. There's another model for the performance of the blade. The performance of the blade depends on a bunch of external parameters, these 4 things in red, and it gives you finally the estimated, I don't want to go into the details of what these parameters are, but the output of this thing is the power of the turbine. So eventually what you care about is the revenue of the operating gas turbine. The revenue depends on a certain, again, on a certain external parameter, depends on the failure temperature, which comes from the lifetime, which comes from the heat transfer, times the power of the turbine, which depends on this bunch of random parameters, times another coefficient, okay? And this is the list of external parameters. We assume of knowing their distributions. And now what we could do, we could simply think the whole system, the 4 blocks, as a giant monolithic thing. And we could just run your favorite UQ method on the single macroscopic system. But because that includes, in this case, 1 PDE and 3 algebraic models, but it could be, I mean, you could easily imagine that it could be 2 PDEs or 3 PDEs or whatever. I mean, building a surrogate for the whole system is expensive, especially if you think of having multiple PDEs. And if any of these blocks were coupled in a feedback mode, you would need to, for instance, run Newton or fixed point iterations. So evaluating one time the big chunk is expensive, let alone doing a surrogate model for that. So the idea to reduce the computational cost is to build surrogates for each component, possibly multi-fidelity, because we know how to do multi-fidelity for a single discipline, is the part 1 and part 2 of my talk. And then we put everything together. So in practice, doing multi-fidelity for each block and then putting everything together, you can think of this as an augmented MISC, where you have not only alpha, beta multi-indices, 1 multi-index for the spatial hyperparameters and 1 multi-index for the sampling parameters, but now you have 3 blocks. There's 1 index that tells you which component you want to refine. For each of these components you want to refine, there's an alpha and there's a beta. So now we have 3 components to add to our gigantic multi-index, okay? The obstacle to overcome to do this is that we don't know the PDF of the coupling variables. So everything would be fine if we knew the PDF of the coupling variables. That we be pretty straightforward to build a surrogate model for each component, but we don't know the PDF for the X's. Now, what do we do? Again, I have, let's say, a decently solid theorem to back this up. It's coming from this paper by Dongbin Chu and others in 2013. But I leave you here the statement. I don't want you to read the statement. This is just for, let's say, purpose of discussion later on. The takeaway of this theorem is that whenever you have epistemic uncertainties, so whenever you don't know the PDF of your random input, it is more important to be accurate in predicting the range of this variable whose PDF is unknown, rather than knowing the actual PDF. So you can get away with a decent estimate, even if you screw up the shape of the PDF, as long as you do a good job in estimating the range of the coupling variables. So, I mean, in a sense, this is a theoretical ground to do the layman thing. The layman thing would be, I don't know anything about the XYZ, I just use uniform PDFs. This is not just a good layman idea, it's just, we also have a theoretical intuition undergoing behind this. So we don't know the PDF, but at least if we can estimate the ranges, we are good to go. And then we can consider all these coupling variable as uniform. We can build the surrogate as if the coupling variable were uniform PDF. So again, we would be replacing PDFs like the black or the red with the gray PDF. Of course, approximating a peaky PDF with a constant PDF, I mean, has a price. The peakier the PDF, there's a constant in that theorem that is larger and larger. The larger is the peak, let's say. But let's say, so now what we do is we do MISC on each discipline, assuming that the coupling variables have uniform distribution. So now it's a matter of choosing which, not only how to refine the disciplines, but also which discipline to refine. And we can do this by tweaking a bit the Gersten-Gribel adaptive algorithm. So the idea would be that we start with a certain surrogate for each block, for each discipline, and then the profit heuristic indicator that tells us which discipline we have to refine considers the contribution of each discipline to the system level outputs. So if improving the system of the heat transfer impacts a lot the total outcome, the final outcome, then we keep refining the heat transfer. If that is good enough for our purpose and it is more important to refine the lifetime model, for instance, then we refine that one only, okay? Because everything is related to the outcome of the system level rather than to the outcomes of each discipline. And crucially, this means that we need to evaluate a bunch of times the outputs of the system level, and that would be very expensive if we did it on the actual models, but we do this on the surrogates. So we start with core surrogates, and then we only evaluate the surrogates to see the changes in the final system level output. So this is very cheap, actually. So, and then so in practice, we start with cheap surrogates. We start refining one of them or two of them, and then each time we refine a model, we rerun we run the surrogates on the whole chain of systems. We see how much the final outcome changes, and then we select the discipline to refine as the discipline that impacted the most a change in the system level outputs. And every time we do this, it means that we have to compute all the profits of all disciplines instead of keeping the profits fixed as you would do for the standard Gersten-Gribel algorithm. And notice that while we keep recomputing the system level outputs, we get a better and better estimate of the range of the coupling variables. So there's a lot of technical details here. I try to go quickly through them, but even if you're lost here, it means that we can tweak the Gersten-Gribel algorithm to keep into account several disciplines, and we refine only the disciplines that we need because they are deemed to have a significant impact on the system level outputs. And this is the convergence that we get and the work allocation that we get. So you see here, this is the total cost in terms of runs that we are running, each run weighted by the cost model of each model. So the red thing here is if we run everything, the four models coupled together as a single block, a black box, I would say, with just one fidelity. Then the green is black box, but multi-fidelity. So we refine everything regardless of the impact of each discipline. And then if you go to instead doing this, let's say, integrated approach where you do separate surrogates for each discipline and then couple everything together, we get the blue single fidelity. And if you go multi-fidelity separate blocks, then we get the black convergence. And here you see that there's a dramatic speed up, yes, and then in particular there's an impressive drop of the error from 1 to 2. And what happens here from 1 to 2 is that essentially the algorithm, this adjusted augmented guessing algorithm, realizes that it's done with solving the PDE. This here is the work allocation per model. So this is the work allocation on the PDE. You see there's 3 fidelities, and then there's the other 3 are just single fidelities because they're just algebraic things. But from 1 to 2, essentially, there's no longer an increase in the number of solves. It's just mostly refining evaluating the downstream, the algebraic component. So the system, the algorithm automatically understands which discipline is useful to be refined if you want to have overall good convergence and limited cost. Okay, so you see again here there's again multi-fidelity heat transfer equation solved on 3 different meshes, single fidelities on the other components, but the work is allocated proportional to the impact. Oops, what happened here? Okay, to each component. Okay, so in conclusion, I have presented MISC, which is a multi-fidelity method that extends sparse-grid stochastic collocation to the case where you have multiple fidelities. We have, I tried to show, I mentioned you that there's this thing is, actually, we have convergence proof in certain cases. It can handle different solvers, and in particular, tensorized solvers, if you have them. So this paper here, a paper with Joachim and Raul, is the paper in 2019 in which we applied MISC to an IGA solver where you have the luxury of having multiple independent discretizations along each spatial domain. So this is the paper where you get that example with 6 indices, 3 random variables and 3 hyperparameters. And this paper by Chiara and the guys in Rome is instead the paper where you use the engineering problem where you have only one index to select the 4 meshes. It can handle also multidisciplines, and the paper is just out here on EJNME with John Jacob and the other guys. And hopefully we should have a MATLAB release soonish of this MISC. The website is going to likely be this one, where if you go there, I mean, you already find the latest release of the sparse-grid kit, which is a MATLAB implementation of sparse-grids for stochastic collocation. You might go there and take a look, by the way. As a black box, I'll say, as a byproduct of this IGA MISC based, I mean, we also proposed a black box parallelization of IGA solvers with Joachim. This is a byproduct of our MISC for PDEs. And with that, I want to stop here and happy to take any questions.
Thank you so much. Thank you, Lorenzo, for a nice talk. Any questions or comments? They bring in the mic to the...
Yeah, no problem.
Alexander.
Hello, Lorenzo. Thank you very much for nice talk.
Hi, Alex.
Just wanted to be sure. Look, I increase level of measure. What should happen with variance? Is it increasing or decreasing? I am asking because I observe numerical diffusion. So on the coarse mesh, my solver doesn't see some features, turbulent features or whatever, if we speak about this Schiff application. And actually, theoretically, I thought that variance should decrease if mesh level is increasing, so mesh become finer and finer. But I think I observed that opposite, that on the coarse mesh variance was small. So can you comment?
Yes, I mean, of course. I mean, this is, if you want, this is very, I mean, Raul also and Joachim there can give you their advice on this. my understanding is that, I mean, MISC is very close to multi-level Monte Carlo, if you want. We're just replacing the Monte Carlo part with a stochastic collocation part. But that doesn't mean that there are, if you want, the same idea that you are, that you should see a decrease in the variance in the deltas is still there. So of course, if you keep increasing the meshes and you keep finding new variance due to this, for instance, to the turbulence, then yeah, you're totally fine. I mean, you're right. There is a problem there. Let me just say that here we are using runs. So I mean, and the ship moves at very low, decently low Froude number, I would say. So there is no much of a turbulence going on here. So what we see here, if your question is this due to turbulence? My answer is no, this is not due to turbulence. This is really due to the fact that the solver, this runs solver, we don't have access to the parameters here, to all of the parameters. In particular, it's a V cycle, and it would jump from one grid to the next grid before the grid it's currently at gets to convergence, because the jump from one grid to the next is due to, let's say, to the norm of a certain residual, but that norm of the residual doesn't necessarily control the convergence of the quantity of interest, right? So the quantity of interest is the integral of the pressure on the hull of the ship. Whether that has converged or not, it's not necessarily, it's only weakly controlled by the control of the residual. So if the residual is at tolerance 10 to the minus 3, the quantity of interest maybe is not yet at convergence 10 to the minus 3. And then you jump to the next grid, but still that error you carry it on, something like this, okay? So it's not a matter of we are discovering more and more variance. It's a matter of a solver. That being said, if we were solving with direct Navier-Stokes, I would say, and we were in a really turbulent regime, then just like multi-level Monte Carlo, also here, I guess you might see some issues. That is my take on this, at least.
Thank you. Thank you.
We have one more question. Shab.
Many thanks, Lorenzo, for the nice talk. So for the multidisciplinary application, how much are you compromised with the regularity of the different boxes in your disciplines, in the sense
Yes.
that, I mean, this kind of method, you care about the mixed regularity when you do the profits, maybe. So how does this affect, I mean, the efficiency of this approach?
Yes. So, I mean, there are the usual concerns about regularity. So you should have, let's say, a good handle on mixed regularity of each block. So it should be nicely behaved. For instance, lifetime should be nicely behaved with respect to Z and C and the mixed regularities. That is, of course, true. So I wouldn't recommend this method if one of these blocks doesn't have enough regularity with respect to the parameters, be them the Z or the Xi. That is one thing. And then the other detail that I didn't touch because I didn't show you feedback coupling. But I mean, I can also, this is also true partially for the feed forward. I mean, here, not only there's issues with the mixed regularity, but also the Lipschitz constants of the model with respect to the previous inputs plays a role. So if the dependence of lifetime on heat transfer on Xi2, which are actually Y1. So Y1 equals Xi2, and that's the input that we put here. If F2 has a large Lipschitz constant with respect to Xi2 or Y1, then whatever error you have in the surrogate model of heat transfer gets amplified by that Lipschitz constant here. And then further in the next. So Lipschitz constants plays a role here because, I mean, it might amplify the errors when you replace full models with surrogates. And then there's also a matter of feedback. So if you by any chance you have two blocks that are linking feedback, then you have to run, for instance, fixed point iterations on the two blocks. And of course, you do that on the surrogate models, but still the Lipschitz constant of that fixed point iteration has to be lower than 1, otherwise the thing doesn't really work, right? And then again, the error is assuming that all the components have Lipschitz constant smaller than 1, such that the overall Lipschitz is smaller than 1, then still the larger the Lipschitz constants, the smaller the convergence of the fixed point. And usually you don't run fixed point up to convergence. You prescribe a fixed number of iterations just to keep it on the safe side on the computational cost. So the error amplifies, right, if you don't really solve the fixed point iteration up to full convergence, if you have a bad Lipschitz constant. So I would say, bottom line, usual requirements on each block, plus considerations on the Lipschitz constants of each component with respect to the coupling variables. Okay?
Roland would like to add to this discussion as well.
Yep.
Ciao, Lorenzo.
Ciao, Raul.
Lorenzo, just following up here, if I understood correctly, there's only one differential equation to solve and the other algebraic, right?
In this case, yes.
Yeah, so in that case, wouldn't you say that the mixed regularity would be connected just to the implicit function applied to the different connections? Because I mean, you get the assumption on the PDE, right? I mean, that you have some kind of convergence with a certain rate. And then for the others, you can take derivatives sort of explicitly almost because they are different functions. So
yeah, of course.
You will have the mixed regularity to apply MISC unless you have a singular point in the implicit function that you're defining on this fixed point.
Yeah, exactly. Yes.
But not in a singular point, you should have the mixed regularity almost automatically.
In this case, yes. In this specific case, you're good to go because there's only one PDE. Yes, the other ones are algebraic expressions, and the feedback here. This is into an exponential, so it's okay. And here, this is a product of things, so it's okay. Yes. So in this specific case, once you have the mixed regularity on the first one, then you're good to go. Yeah. In general, you might need to do the same analysis block by block, of course.
Sure, and then one has to see the coupling in a different way if you have different PDEs. But I think in this case, because of this structure,
and also let me add that here we're thinking of if the two blocks were PDEs, we're thinking of two blocks that exchange a handful of numbers. So we're not thinking, for instance, of a fluid structure interaction where there's a whole field going from one to the other, right? This setting works well. Right? If you have only a handful.
And this may simplify the mixed regularity analysis too.
Yes, exactly. Yes. Now I have ideas on how you would accommodate the case of having a field from one model to the other, but that's food for future research.
Okay. Thank you.
Any more questions? Okay, so let's thanks again, Lorenzo, for the nice talk.
Thank you for having me. Thanks.
Okay, so now there will be a small break and the next talk will be in 15.
Okay. Bye.